Okay, so now that you know how to find the determinant of a matrix, we're going to use that to help us find the inverse of a matrix. Now, before we get into the actual calculating, we have to understand what an identity matrix is. An identity matrix, first of all, has to happen on a square matrix only. And you'll notice that there's a pattern. The main diagonal is filled with ones, and every other entry is just zero. So I don't care if it's a 2 by 2, a 3 by 3, or a 4 by 4, as you look along this main diagonal, they're all ones, and then every other entry is going to be a zero. So that's going to be super important in proving that two matrices are inverses of each other. So this right here, this is what it's all about. If you have to prove that two matrices are inverses of each other, you have to show that when you multiply A times B, it gives you the inverse matrix. You have to also show that if you multiply B times A, so the reverse, it also gives you the inverse matrix. So that's what we're going to do in example 1, because that's how your assignment is set up. So the first thing we're going to do is we're going to find A times B and show that it's the identity. So the setup, again, we're going to do the t-chart, and it's rows times columns. So A is first, so it has to go this way. So it's 2, -1, and then it's -3, 1. And B is second, so that has to be the columns. So it's going to be -1, -3, and then it's going to be -1, -2. So then we do our multiplying. 2 times -1 is -2. -1 times -3 is +3. Then we have -3 times -1, that's 3. And then 1 times -3 is -3. And then if we do 2 times -1 is -2. And then -1 times -2 is +2. And then finally, -3 times -1 is 3. And then 2 times -1, or sorry, 1 times -2 is -2. So if you work this all out and simplify, we end up with +1, 0, 0, 1. So far, so good. That is the identity. So now we have to do it the other way. Now I have to erase my writing up here at the top, because if we're doing B times A is done just a little bit different. So since B is first when we make our t-chart, that means that B has to go across. So it's going to be -1, -1, and then -3, -2. Then across the top, A has to be vertical, so we're doing the columns, so it's 2, -3, and then the second one is going to be -1, 1. So we do our multiplying. -1 times 2 is -2, and then -1 times -3 is +3. And then we do -3 times 2 is -6, and then -2 times +3 is, it's -2 times -3, that's a +6. Then we do -1 times -1 is +1, and then -1 times +1 is -1. And then we do -3 times -1, it's +3, and then -2 times +1 is -2. So if we simplify all of this stuff, we end up with 1 for the first spot, 0, 0, and 1. So since it checks out in both directions, now we can say that they are inverses of each other. Okay? Now, that wasn't calculating if it's the inverse. So what we're going to do now is we're actually going to calculate an inverse. Now, there's different rules for the different sizes. So the inverse of a 1 by 1 is just the reciprocal. And I should also mention the symbol for an inverse is just, it looks like a -1 power. So I'm going to just do a quick example here. If I have a matrix that's, I don't know, let's say 3, and I want to find the inverse of 3 is just the reciprocal. And a reciprocal is when you take a fraction and flip it. So I'm going to make that 3/1. If I flip it over, that's the answer. So a 1 by 1 is super easy. You just have to remember to flip it into a fraction. If it's already a fraction, that's even better, because then you just flip it. If it's not a fraction, you make it a fraction. Now, if you're going to calculate the inverse of a matrix, see, it requires the determinant. So you're going to have this fraction with the determinant down at the bottom of the fraction. There's always going to be a 1 on top. and then you have to do the adjoint of A. Now, I don't care about the vocabulary. I just want you to notice the pattern. The pattern is you have to switch places between these two numbers, so they flip-flop, and then B and C stay exactly where they're at. You just flip their signs. So you take the fraction that's in the front, you apply those changes to your matrix, and then you just distribute it by the fraction. And sometimes you'll have like a lot of fractions in your answers, which is okay. So we're going to go ahead and hit that up. So the first thing I want to do, since I have to find the inverse, I want to find the determinant. So my determinant, let's do the determinant of this guy. So the determinant would be this multiplied together. So that's going to be 6. And then we multiply these two together, and that's going to be 2. And then we subtract them. So if I find the determinant of this, my determinant is 4. Now, we use that to calculate the inverse. So that determinant has to go at the bottom of a 1, and then we have to create that adjoint matrix, which basically is another pattern you just kind of have to remember. So the pattern for this is switch these two. So I'm going to put 2 right here and 3 right here. And then for the other two, you just got to flip their signs. So this -2 becomes a +2, and this -1 becomes a +1. So then the final answer, you just have to take your 1/4 and do your scalar multiplication, which means you just distribute into the entire matrix. So our final answer for this inverse is going to be 1/2, 1/2, 1/4, and 3/4. And as I mentioned before, a lot of times when you find inverses, because you have this fraction out in front, sometimes you'll end up with a lot of fractions inside your final answer. So that's our final answer. And I'll show you that again because I know it's confusing. So this one wants, again, find the inverse. You notice if it says if possible, there's a reason for that. Because we have this fraction, that fraction, when you do AD minus BC, it cannot equal 0 because there is no such thing as dividing by 0 and it's undefined. So if that happens, that's why we're saying if it's even possible. If you end up with a 1/0 when you calculate your determinant, well, then it's not possible. You don't even have to finish the problem. Okay, so here we go. So I've got this guy right here. I've got to find the determinant first. So that determinant is going to be -8. And then we do this guy right here, and that's going to be another -8. And then we put a minus in between. So because we have that double minus, 2 minuses turn into a plus, and then that gives us 0. So you can see this is exactly what I was talking about. If we were to continue, we would end up with 1/0, which is bad, and I don't even have to finish this. The fact that that has a 0 means that this is not possible. Okay? So that's how you do a 2x2. And so I'm going to just, I'm going to pause for a second, or you can pause the video, but I'm going to give you a second to copy this into your notes because this is how you do a 3x3. Psych! So we're not going to do 3x3s. That's crazy talk. We're just going to use a calculator. So for anything larger than a 2x2, and remember, it has to be a square matrix in order to calculate that inverse. So anything bigger than a 2x2, like a 3x3, a 4x4, these ones get pretty intense, so I'm not going to make you learn how to do that. So how would you do that in the calculator? It's pretty simple. You go into your calculator and you put in your matrix, and then you just raise it to the -1 power. So for example, that same exact question, if I was going to do it in the calculator, I would hit math, I would hit matrix, and because this is a 3x3, I hit F2, so I'd enter 1. Oops, I can't hit enter, I have to use the arrows. So 1, 1, and then I would put, let's go back over here, 3, 5, I missed a 3. And then we would put 4. And then it's 0, -1, and 0. So we go outside of the matrix, and we use the caret key right next to the x² button, and we just put it to the negative first power, and bam, you'll notice it gives us the same exact answer as we have right here. So again, 3x3s, 4x4s, they get intense, and I'm not going to hold you responsible for doing all that stuff. So you can just enter those into the calculator, but your 2x2s must be done by hand. So that's it. That's all all you have to know for inverses.